Right, so now we've met the chain rule, the product rule, and the quotient rule, plus all the standard results that we've derived from them. Let's just have just take a step back and have a look at what we've covered so far. So we've got the chain rule in the left-hand box, we've got the product rule in the middle box, and the quotient rule in the right-hand box. And this would be with respect to the products and the quotient rule, this would be how they would be presented in textbooks and in formula booklets. So I'm talking about a differentiation toolkit now. These rules are at your disposal to use to various situations, okay? And it's up to you to decide which rule to use, which would best suit. And also, is there any, are there wider options? Could you use the product rule as opposed to the quotient rule, and or vice versa? So that there's things that you have to be aware of, and these things come with practice. The more questions you do, the better you will be at using these three rules. So I have a task for you. This is task A. There'll be another task later on, and what I would do is I would just pause the video and have a go at the task. And what you have to do is use the differentiation toolkit, everything you've learned so far, and you're going to differentiate the trigonometric functions that I presented here. So we have tan x, which we've not looked at yet, cosec x, sec x, and cot x. Okay, and what I've done, I've given you the solutions at the bottom, okay, but I've not told you which solution corresponds to which derivative. It's up to you to determine which of these solutions matches which of those derivatives. It's just to give you a guide as to whether you're on the right lines or not. Okay, so I would recommend think about your differentiation toolkit and pause the video and have a go at the four derivatives, and I'll go through them momentarily. Okay, so let's have a look at the solution to task A, part 1. So we have to differentiate tan x. And just so you're aware, I might do these in a particular way that you haven't used, but you get obviously the same result. That's fine. This is going to happen because it's a toolkit. You can't sort of predetermine in every case that you have to use particular tools for particular jobs. That's not how it works. So when I look at tan x, and I think, how is it defined? I'm thinking of identities here, and I know that tan x I can write as sine x over cos x. And because it's an identity, they are identical statements, aren't they? I've not changed anything about the derivative that I'm going to find. If I differentiate sine x over cos x, it's identical to differentiating tan x. So I'm going to define my y as sine x over cos x. Once you've done that, one of the rules should be leaping out at you, shouldn't it? We've got a fraction, haven't we? So I'm thinking, if I've got a fraction, why don't I label the numerator number 1 and the denominator number 2? And if I do that, of course, this is telling me that I'm going to be using the quotient rule. Okay. The quotient rule, I think, is the most obvious because you can see fractions in front of you, and chain rule, I think, and product rule can be more subtle, but the quotient rule is probably the most obvious. So let's just write down the 4 pieces of information we need in order to differentiate this. So the first thing to do is, of course, to write down the 2 functions themselves. So it's sine x and cos x. So we'll do that. So sine x, cosine x, or cos x, and then we have to differentiate them. So we're going to have the derivative of 1 and the derivative of 2, and they are standard results. Okay, so the derivative of sine x is, of course, cos x, and the derivative of cos x is negative sine x, so just be careful with that. Okay, and we can now use the quotient rule. And just let's remind ourselves how it looks. So we take the second function, we multiply it by the derivative of the first function, and then we subtract the first function multiplied by the derivative of the second function. And say to yourself, 2 diff 1 subtract 1 diff 2, or 2d1 subtract 1d2, however you want to do it. Great. So I'm just going to partition this off. So dy by dx, let's do this. Dy by dx is going to be, let's put everything in. So we do the diagonal multiplication. So function 2 multiplied by the derivative of 1. So that's going to be cos squared. Oh, so that's interesting. It's an interesting start. So we've got cos squared x. Okay, great. And now we have to subtract the opposite diagonal. So we have to subtract sine x multiplied by negative sine x. And as we saw in example 2 from the quotient rule, we have a negative there. So, and I'm subtracting this. So the double negative is going to give me a positive. So this is going to be plus, and I'll put that in red so it's really clear, plus sine squared x. Right. So that's an interesting start already, isn't it? Cos squared x plus sine squared x in the numerator. All over. And now we're going to take function 2 and square it. So function 2, which is of course here, is cos x. Square that, we're going to get cos squared x in the denominator. So cos squared x. Isn't that nice? Now, doesn't look like any of the answers we've got so far, but we should, I say we, you should be fully aware that we can do something with this. Standard identity introduced last year, or in year 1 in your case. So we can replace all that with 1 over cos squared x. Now then, we now have a reciprocal trig function. 1 over cosine. Okay, if we use the third letter rule is, of course, or the first letter rule if we're going backwards, is of course going to be sec squared. So this is equal to sec squared x. All right, and you can actually differentiate. If you differentiate tan x from first principles, you'll get to the answer in a completely different way, but just as interesting, I think. So that's number 1. Now for cosec x, we've got to differentiate this now. Once again, how could we think of cosec? Well, we don't have any standard results for cosec, but what we do have is a standard result for its reciprocal. We do know something about, so I'm using the third letter rule here, 1 over sine x. Okay, we can say something about that. So I'm going to let y equal 1 over, let's rewrite that, it's a bit scruffy. So 1 over sine x. Now then, once again, it's a reciprocal trig function. I can still use the quotient rule because I still have a fraction presented in front of me. Even though it's just 1, that's okay. We can differentiate 1. In fact, it's a very easy expression to differentiate, isn't it? So we've got 1, and then we've got sine x in the denominator. So we'll put that in as well. That's going to be number 2. So it's another quotient rule question. So let's write these out, 1 and 2. Okay, and we'll just write down what the functions are. So of course, it's going to be 1 over sine x, like that. So as it appears in the fraction. And the derivative of each of those is very straightforward indeed. So derivative of 2. If I differentiate each of those, of course, the derivative of 1 is 0. It's a constant which will disappear. And the derivative of sine x is, of course, cos x. Okay. Now, we can apply the diagonal multiplication and using the quotient rule now. So it's going to be function 2 multiplied by the derivative of 1. So let's write down dy by dx now. Okay, so if I do that, I'll write it out, but obviously this is going to be 0, isn't it? The term dies because we're multiplying by 0. And then we subtract, okay, the opposite diagonal multiplied together. So this is going to be 1 multiplied by cos x. So that's going to be subtract cos x. Okay, and that's going to be all over function 2 squared. So that's going to be sine squared x. Okay, right, let's just tidy this up now. So this is going to be negative cos x over sine squared x. So there's a bit of a clue here with the negative sign, isn't there? All right, so how can I think of this? Well, if I just as a little aside here, I could think of this as negative cos x over the product of sine x and sine x, sine squared x, isn't it? And you'll notice if I write it like that, it's essentially the same as negative cos x over sine x multiplied by 1 over sine x. Okay, now this is where you need to know your identities. We have cos over sine. Now remember, this is the reciprocal of tan. In other words, this is cot, that's cot x, and 1 over sine, of course, is the same as what we talked about right at the beginning. So if you don't know what 1 over sine is, you probably should do, because that's how it was defined at the beginning. 1 over sine x, which is here, the thing you differentiated, is the same as cosec. Okay, so that's our answer. So we now know that this is equal to negative cot x cosec x. So there we have it. So that's the derivative of cosec. Okay, so we've eliminated 2 of our possible answers. So as we can see at the bottom, so we've now accounted for. So I wrote it the other way around, but it was negative cosec x cot x. We've got that. We've also used sec squared x. So we have 2 left over. Let's see which one's which. Great. So once again, we have a reciprocal trig function. I'm going to use that 3rd letter rule. This in case you haven't learnt these identities. It doesn't matter that much, but it's better if you know them, as I keep saying. You need to have them at your fingertips, really. So I can define y as 1 over cos x now. And you might have got to a stage, if you've watched a couple of these solutions, having tried task A and not really got very far, maybe pause the video again and then try the questions 3 and 4. Now you've seen a couple of examples. So once again, I'm going to define the numerator as function 1 and the denominator here as function 2. So that will obviously indicate we're going to use the quotient rule again. Okay, so let's write out our 2 functions. So as it appears in the fraction, so it's 1 over cos x, so it's going to be function 1, function 2, and it's going to be 1 and cos x, like that. So this is going to be the derivative of 1 and the derivative of 2. So if I differentiate 1, of course, we got the same result as last time. That's going to become 0. It's a constant. And the derivative of cosine is, of course, negative sine x. Just be careful with that. It's a standard result, but it's negative. And let's apply dy by dx. And we're going to use the quotient rule again. So we've got that diagonal multiplication. So we start with function 2, multiply by the derivative of 1. That's going to be 0, but we'll put the working in anyway. So cosine of x multiplied by 0. And again, just a warning, we are multiplying 1 with a negative amount here, negative sine x. And because it's a subtraction, that's going to create a plus. 2 negatives make a positive. So plus sine x. Okay, hope that's clear. Okay. And all over function 2 squared. So that's going to be cos squared x, like that. Okay, great. So like I said, that first term is going to be gone. So we're going to be left with sine x over cos squared x. So the question is, which of these other two options have we got? Well, a good thing to do, like I did in the previous example, let's just split this up a little bit. So I know it's going to be sine x. I've got a cos x as well in the denominator. So that looks like tan to me. And then if I multiply that by 1 over cos x, which is accounting for the cos squared in the denominator, so that's the same thing. We can see that we've got tan x multiplied by 1 over cos x, which is, of course, sec. So there we have our answer. So this is simply, so the first bit is, of course, this part here is, of course, tan x, which should give it away. And I've written it the other way around, but it doesn't matter. Multiplied by 1 over cosine as defined up here, which is, of course, sec x. Doesn't matter which way around you write it. Great. So sec x tan x is gone. We are now left with negative cos x squared. So this must be our final result. Let's just verify this. How do we define cot? Well, you could write it as 1 over tan. But we don't yet have a derivative for, well, I suppose we could. I'm just thinking, should I try something different? No, I'll stick to my plan. Let's write this as cos x over sine x. Okay, not the time to experiment when you're recording a video. So cos x over sine x, we'll label those 1 and 2. So this is going to be 1, that's going to be 2. Let's just label them now. So 1 and 2, and then let's write down the derivatives of each of these functions. Again, nice standard results here, so nothing to worry about. So we've got cos x, sine x, the derivative of cos x, and the derivative of sine x. And should be pretty clear now what's going on. So this is going to be negative sine x and cos x. And once again, it's been all quotient rule, this, hasn't it? Didn't know that to start with, but that's how it's turned out. So differentiate 2, beg your pardon, sorry. Say that again, function 2 multiplied by the derivative of 1, going diagonally. Okay, so we've got a negative now, so that's going to be negative sine squared x, okay. And then I have to subtract the other diagonal, so subtract cos x multiplied by cos x. So that's going to be negative cos squared x all over function 2 squared. So that's going to be sine squared x. So at first glance, you might be thinking, how could we do this? There's a couple of ways of doing this, actually, from where we are. We could split it into 2 fractions, or we could notice, which is what I'm going to do now. If you look at the numerator, this is essentially sine squared plus cos squared, all multiplied by -1, isn't it? So I could simply just take out a negative sign and write sine squared x plus cos squared x, and we know that's identical to 1 from the identity over sine squared x. So this is equal to negative 1 over sine squared x. And we know that 1 over sine is, of course, cosec. And because it's squared and negative, this is clearly negative cosec squared x. Just while I'm mentioning that, I might just as well tell you about just the idea that I was talking about. If you split this up into 2 separate fractions, the cancellation will, of course, give you, you'd have negative sine x over sine squared, sorry, negative sine squared over sine squared, which is, of course, negative 1. And then you'd be subtracting cos squared x over sine squared x, like that. Okay. Now, the second term that you've got there is, of course, cos over sine is, of course, cot. That bit is cot. So you've essentially got this. You're going to get negative 1 subtract cot squared x, which is equal to minus 1 plus cot squared. Now, if you know your Pythagorean identities, you'll know without too much trouble, hopefully, that everything in that bracket there is identical to cosec squared, and then the minus takes care of itself. Okay. So there's different ways to get there, but we've now eliminated all the answers. We've just verified all these results here. Okay, so let's see what's next. So we can now apply what we've discovered in task A through our derivations to write down some new standard results for tan and, of course, the reciprocal trig functions. So we know that the derivative of tan is, of course, sec squared. I'm just going to leave it like that for now. If we differentiate, I'm going to do cot next, because cot and tan are linked together, and they're the derivatives that only contain a squared trig function. So if you remember from the derivative, cot differentiates to negative cosec squared. So I'm going to put the negative sign here, and I'll put the cosec squared in as well, just to remind us. I just do that because that's how I remember. I just remember that tan is a squared, it's sec squared, and also because cot and tan are reciprocal, cot is cosec squared. It has another squared in it. But you'll probably come up with your own ways of remembering these things. Not that you have to, but I'll get onto that in a second. If you differentiate sec, of course, you get sec x tan x. That would be the derivative of sec x. So again, I'm just going to write it as sec and tan, like that. And the derivative of cosec, which was the only other one that we looked at, we get obviously negative cosec. So it's a negative. And rather strangely, we also have a cot in there as well. Okay, so I've done those two separately. If you notice, if you differentiate sec, the sec appears again in the derivative. Okay, so that's why I isolate those two. And same with the cosec, derivative of cosec, the cosec appears again. And then you get a tan and a cot, respectively. Just some way of remembering it. Now, because we've got standard results for tan x, sec x, etc., what if we bring in this coefficient again, which we did when we did the chain rule examples very early on? Well, the same thing happens. So if I want to differentiate tan of kx, once again, we retain the kx inside the function, but the coefficient also duplicates and migrates to the front as a coefficient of the whole function. So the derivative of tan kx is going to be k sec squared kx. Okay, and then moving through the rest of them, we retain the kx for cosec and for cot here, And even though it's appearing twice, it doesn't matter. The constant just moves once to the front. So we have negative k, cosec kx, cot kx. And we'll fill in the other two as well. So if we do sec of kx, tan of kx, the k migrates to the front. And similarly, cosec squared kx, and the k goes at the front. Now, once again, I've alluded to this already. You don't have to remember these. These are standard results that are provided for you in the formula booklet. But it's good to know how to derive them because you're applying your knowledge of the quotient rule and a few other things. And it's also a good way of ingraining the knowledge as well by actually going through the process. You understand where it comes from a little bit more. So now we're going to move on to differentiating inverse trig functions. And we're going to use this result that came up earlier in the chapter, whereby we can represent the derivative dy by dx as 1 over the derivative of dx dy. All right, so we're going to use that idea, and I'm going to let you have a go first. So task B, we're going to use the special case of the chain rule, which we've just talked about, and you're going to find the derivatives of each of the following inverse trig functions. So I'll just clear this and let's have a look at what I'm talking about. So for task B, here we have it. So the derivatives of arc sine of x, arc cos of x, and arc tan of x. Once again, I've provided you with the solutions at the bottom. So I would pause the video now, if I were you, have a think, use the special case of the chain rule, 1 over dx dy, and see if you can arrive at these results. Once you've done that, okay, unpause the video and then we'll go through the results together. Right, so this is quite tricky. It's sometimes hard to know where to start with this. And if you had a few problems, perhaps just watch the first few steps and then repause the video and try again yourself. So you just have to be clear about what arc sine x actually means. We know it's an inverse trig function, not a reciprocal. Please do not confuse the two. They're completely different things. I'm going to write it in a more familiar sort of way. So remember that y is, if it's the inverse sine of x, I can write it like this. And it's the function you use on your calculator all the time, isn't it, to find things like principal angles. But how does this bring in the dx by dy? I've given you a tip here that we're going to be using the special case of the chain rule where we're differentiating x with respect to y. So the question is, how does that appear in this question? Well, we don't really know much about this inverse sine here. It's a strange looking function. But what I do know is that if I applied the sine function to both sides of this equation, sine and sine to the minus 1 are obviously inverse functions. They will undo each other, okay? So I can do that without changing any characteristics of this equation. So if I take the sine of both sides, so I take the sine of y, and I take the sine of the right-hand side, then this opens up some possibilities. Okay, so the sine of y is equal to the sine of the sine of x. And perhaps it would be better just to put this in brackets, but what you'll notice is that because I've done that, the sine and the inverse sine will cancel, and I can rewrite this as sine of y is equal to just x. And remember, you already knew this in a way, we just haven't looked at it like this. When I mentioned principal angles a moment ago, y is the angle, okay, and x is the trig value. Remember, to find the principal angle, you use the inverse sine function to get y. All we've done is just undone that step and gone one step backwards. So we've now got a situation where we've got sine y equals x. Right. So how does this help us? Well, I can now just differentiate, but I'm going to be differentiating the function x with respect to y this time, because x is now the subject of my equation. So to make it more clear, perhaps I should write it in the reverse order. So x is equal to sine y, and then we just differentiate x with respect to y. And we can do that in one easy step. So dx by dy, where y is now the independent variable, is just going to be cos of y. Okay, so that's dx by dy. The problem is I want dy by dx. Well, that's okay. I just use the reciprocal. So dy by dx is equal to 1 over the cosine of y. Still doesn't look like any of those solutions I provided. What's going on? Or what's the problem, more importantly? Well, the problem I have, and sometimes it's a problem, sometimes it isn't. It depends on the context. My dependent variable y is now appearing as the function on the right-hand side. So what I mean is my derivative is now a function of y. You'll notice that all my derivatives down here at the bottom are all functions of x, okay? As derivatives with respect to x probably should be, okay? There's nothing wrong with my answer, but it's not a function of x. So how on earth am I going to get a function of x out of this? Well, we go back to our trusted trig identities, and we've just and without knowing it, we've written down something really important already. We have stated twice, in fact, so here and here, that x is identical to sine y. So do I know an identity that links sine and cosine together and nothing else? Well, of course I do. I know that sine squared, I'll just write it in terms of how it appears in the textbooks and the formula booklets and things like that. We know this, don't we? This is an identity true for all values of theta. So therefore, in this situation, I know that it doesn't matter what I call the angle, sine squared y plus cos squared y is identical to 1 also. Doesn't matter, does it? But I know something about sine squared y. I know that sine squared y is exactly the same as, because it's here, it's exactly the same as x squared, isn't it? Okay, so now I've called this something specific, so I now know that x squared, in fact, I'll do that in a different color because I've made a substitution. So I now know that x squared plus cos squared y is equal to 1. Okay. Now then, if I rearrange, we now know that cos squared y is equal to 1 subtract x squared. And all I have to do now is take the square root of both sides. And I now know that my cos y here, and when I say here, you can't see where I'm pointing, my cos y here, I can now replace with the square root of all this. So with that little bit of an aside there, I'm just going to partition this off. I now know that dy by dx is simply going to be 1 over the square root of everything I've just found here. And I apologize, I'm just running out of space. Okay, so that's the derivative of arc sine. Now, if you had started this and didn't really get very far, maybe try the next two before watching the full written solution. Okay, so for the next part, we're going to use the same process. So I'm going to rewrite the equation as y is equal to the inverse cosine of x. And if I apply the cosine function to both sides, as I did with the sine function in the previous question, so I've got the cosine of the cos to the -1 of x. They obviously undo each other. So we now have the cosine of y is equal to x. And you'll remember, of course, this is a very important property because we might be able to use this in an identity later on. Now, to differentiate dx by dy, we use the standard result for cosine. Obviously, this is with respect to y, so that's going to equal negative sine y. Okay? And once again, to find dy by dx, we just reciprocate that. So dy by dx is just going to be the negative version of 1 over sine y. It doesn't matter where you put the negative, by the way, we'll put it on the outside like that. So negative 1 over sine y. It's probably revealed what the prime candidate is for the solution as well, okay? But we'll just go through the remaining steps. Once again, we can use a trigonometric identity. So I'm just going to do that over here. Make sure I don't run out of room this time. So we know, of course, that sine squared y plus cos squared y is identical to 1. Okay. Now, that also means that if I substitute in cos y in this case, which is here, for x, I'll get the same result essentially as I did previously. So the cos y is going to be replaced with x squared, like that. Okay, and just to reiterate this, if it's not clear, because I've called the cos y something specific, and we could argue about this, because the arc cos and the arc sine functions are only defined between certain values because they have to be 1-to-1. I can't really say it's an identity because not all x values will be valid in this instance. Okay, it's not true for all x, but that's just a technicality I don't really want to get into at the moment. So we're going to have 1 plus the x squared would be equal to, so I'm dropping the identity there. It's just an equals. Oh, I've just realized I've done that wrong. Sorry. So sine squared, I apologize, sine squared y plus cos squared y is equal to 1. And then rearrange that. So therefore, sine squared y will be equal to 1 subtract x squared. We can now substitute that in, or well, we'll take the square root first of all. So sine of y is equal to the square root of all that. There we go. And substitute everything in. So once you've done one of it kind of falls into place, doesn't it? So the 1 subtract x squared will be replaced to sine y here. So we've now got the final answer. So dy by dx is simply going to be negative 1 over the square root of 1 subtract x squared. Okay, so that's the derivative of arc cos. Quite a surprising result, I think you'll find there. Okay, no trigonometry involved, which is interesting. And the final one, we've got arc tan. And once again, now you've seen a couple of examples, perhaps pause and try this for yourself. So again, I can breeze through this a little bit quicker, I think. We have the arc tan function, which is, of course, tan to the power negative 1 of x. And if I apply the tan function to both sides, we will get tan y is equal to x, okay? And we differentiate with respect to x. If we do that, we get dx by dy, and we can now use our new result for tan. Dx by dy, now that was sec squared y. Okay, and once again we reciprocate, so therefore dy by dx will be 1 over this. Right, so the problem we've got is we've got a denominator which looks completely alien to what we're supposed to have. We need a function of x. Well, where's the important part? The bit that we've been substituting in every single time appears when we write down x as a function of y. So we saw the connection in the first two. We saw that when we, in the denominator, when we had cos y here and we had x equals sine y, we need an identity that connects the cosine and the sine together and nothing else. Once again here, when we had the sine y and we had cos y here, we need an identity that connects the two and nothing else. The same one, sine squared plus cos squared is 1. In this instance, we have sec squared y and we have tan y. And we need an identity that connects the two and nothing else. Well, we have one. We are very fortunate because we know that one of our latest, I would say, Pythagorean identities is as follows. We know that sec squared y in this instance is identical to 1 plus tan squared y. Okay, it's an identity from year 2. So that's really good news. So I can now just replace, so the sec squared y will be equal to, in this instance, 1 plus tan squared, which is of course x squared. Okay, making the substitution, we've now got our answer. So all of that on the right hand side can now replace the green starred part that I've just labeled. So final answer, dy by dx is going to equal 1 over 1 plus x squared. No square root this time. Okay, so those are the derivatives of the inverse trigonometric functions. Okay, so now we've differentiated some other trig functions, those reciprocal ones, and we've also differentiated the inverse trig functions. We're just going to do an example where we apply some of the knowledge we've just come across. So we've got a function here. We've got y equals tan, beg your pardon, 2 tan x multiplied by cosec 3x. So again, we've got to go back to our differentiation toolkit. And what does this suggest we need to use? Well, at first glance, I look at this and I think, well, I've got the 2 tan x. First of all, that could be a function on its own, and so could the cosec 3x. So I'm thinking maybe using the product rule here. So let's have a go with that. I think that's probably a sensible choice. So we'll label this as 1. We'll label this as 2. And we'll find the derivatives of those separately. So I'm just going to write them out again. So we've got function 1, function 2, like so. And we've got 2 tan x and cosec 3x. So just be a bit careful with that. All right, and then we do the derivatives of each of those. So the derivative, so differentiate 1 is what the diff stands for, and differentiate 2. Put that in there as well. Okay, now let's have a look at these two separately. Tan, of course, is a standard function. It is now because we know how to differentiate it. And the 2 coefficient just remains as it is. So this is going to be 2 sec squared x. Remember, of course, when I did this initially with sine and cosine. I put the sine and cosine in brackets just to show which bit we're differentiating, and the coefficient remains the same. And now we've got cosec 3x. So we're going to have to use one of our new standard results here. So I've got to be a bit careful about this 3x here. So I know that cosec, based on the standard results, is going to give me negative cosec, and it's going to give me a cot as well. All right, so that's from the standard result that we met earlier. And remember, of course, we're dealing with 3x. So this is cosec 3x here and cot 3x, don't forget that. And the derivative obviously moves to the front, which is, of course, 3. So that gives a coefficient of 3. Okay, so let's apply the product rule now. So the product rule tells me I have to take the product of the diagonals and sum them. So if I start with function 2 and go diagonally, so we're consistent all the time, and then I multiply that by the derivative of function 1. So we have consistency as well, remember, with the quotient rule as well. So dy by dx is going to equal the product of those two. So I'm going to move the 2 to the front, and I'm going to write this as sec squared x cosec 3x. Okay. And then I'm going to add the product of the opposing diagonals. So 2 tan x and all this here. So that's negative 3 cosec and the rest. And just be careful here, of course, because we have a negative sign in front of the 3. And if I'm adding this, then this is obviously going to be a subtraction. So it's going to be subtract, let's write it all out, 3 cosec 3x multiplied by cot 3x. Okay, just fits on nicely. That's it, essentially. We can also factorize out if there's common factors. Let's see what the common factors might be. Well, 2 and 3 are co-prime. They don't share any common factors. Cosec 3x, though, appears in both terms. So let's factor it out. That might be useful, of course, if you have to find stationary points, you know, where you have to factorize and then set it equal to 0. That can be useful in that situation. So it's good to do this. Cosec 3x, and then we're going to have 2 sec squared x subtract 3 cot 3x. Okay, so that's just an example of how to apply just one or two of these standard results. Okay, so that concludes the lesson.